Good afternoon, TechNation. Welcome to Webinar Wednesday. Today's presentation is eligible for 0.1 CE credits from the ACI. To get us started, let's give away one of our TechNation Tour t-shirts to the first attendee who can tell me what city and state is home to the corporate headquarters of today's sponsor, Conquest Imaging. Answer now using the questions feature on your dashboard. While you are answering, TechNation would like to thank Conquest Imaging for their support of our Webinar Wednesday series. Conquest is the largest supplier of ultrasound parts, probes, transducers, probe transducer repair, training, service, and free 24/7 technical support. For more information, visit conquestimaging.com. So let's take a look at the responses that have come in, and our winner of our TechNation Tour t-shirt is Dave Minke, CBAT. Congratulations, Dave. We'll get your information at the conclusion of the call to send out that t-shirt. The next stop on our 2016 TechNation Tour will be the MD Expo in Dallas, Texas. It's April 21st to the 23rd. Conquest Imaging has included a VIP pass in today's workbook, which can be downloaded from the handout section in your webinar dashboard. The VIP pass will give hospital employees complimentary admission to our 3-day conference and expo. Today's presenter is Jim Rickner, the training director for Conquest Imaging. He has over 20 years of experience working on a variety of electronic equipment. His experience includes repairing and operating flight simulators, specialty aircraft avionics, destructive material testing equipment, and a variety of ultrasound systems. He has worked for Conquest Imaging for over 9 years and was a senior field service engineer prior to becoming the training director. Jim, you may begin whenever you're ready.
Thank you, Kristen. I want to thank everybody for attending today, especially TechNation for sponsoring Webinar Wednesday. This is an outstanding opportunity for all of us to get together and increase our knowledge across a variety of products. So thanks everybody for taking time out of your busy day. Today we're going to talk about NFPA 99 from an electrical safety testing perspective. I think it's a very important subject, and we'll discuss a little bit about why. Why do we want to comply? Why should we comply? Well, hospitals are hazardous environments. As much as we want to say, well, they're really safe, they're very hazardous. They have bottled oxygen, they have anesthesiology gases, all types of electrical equipment. There's a lot of hazards that we need to account for. And just some statistics from 2006 to 2010, they averaged 6,240 structure fires per year, 6 civilian deaths, 117 civilian injuries, and $52 million in property damage. That's per year. That's fairly significant. And from a Biomeds perspective, we can actually lower these numbers and have a very positive effect when we talk about risk management. And that's what NFPA does for us. NFPA 99. It establishes criteria based on risk to patients, staff, and visitors to minimize the hazards of fires, explosions, and electricity. Now, obviously, these structure fires and deaths aren't all caused by electrical safety failures, but some of them surely are. So let's talk a little bit more about it. There are 4 levels of risk categories associated with NFPA 99. For the different systems. Category 1, the systems are expected to work or be available at all times to support patient needs. This is the highest level, the most critical category as far as risk categories go. Category 2, systems are expected to provide a high level of reliability. However, limited short durations of equipment downtime can be tolerated without significant impact on patient care. Category 2 systems support patient needs but are not critical for life support. And so that's really the key point between category 1 and 2 is that they're not critical for life support. However, they still play a very important role in patient as far as patient needs go. Category 3, these are just normal building systems where the reliability, or is expected to be what a normal, computer would be in an office building. There's still equipment that has or supports patient needs, but failure of such equipment would not immediately affect patient care. And it's definitely, the last point, it's not critical for life support. So important to know. Category 4 have no impact on patient care, and patients would not notice or have any discomfort in event of a failure. Now, these category applied equipment operations and are not intended to consider intervention by caregivers or others. What that's saying is, for example, you have a ventilator and it's considered a category 1 and it fails, where you could have the physician, the doctor, give manual ventilation, but that's not considered a backup. So it's not intended that these categories be misunderstood with a caregiver giving some kind of care or trying to cure the patient through that. So a risk assessment should be conducted to evaluate the risks to the patient, staff, and visitors. If you go into NFPA, it gives very specific criteria for risk assessments to be conducted, and we just don't have the time in this presentation to discuss that, but it's in there. After you talk about risk categories, there are also what they call essential electrical system categories. There's type 1 or type 2. And what this essential electrical system says is that you have to have at least 2 independent power sources, and at least one of them must be located on site. We all have different, main power supply companies in the area. For example, California, we have Pacific Gas and Electric Company, or that could be one independent power source coming into the hospital. But in addition to that, you'll have to have a generator located on site that can provide power in the case of electrical failure outside. So we want to be careful, or be aware of that. It says corresponds to the risk categories assigned. In other words, what we're saying is type 1 is assigned to a risk category 1, and a type 2 is assigned to a risk category 2. And the biggest difference between them, and I'll show you a slide after this, type 1 and type 2 is that a type 2 does not have what they call a critical branch of care. There's 3 branches, and again, I'll give you a slide on the next one. And type 1 has the critical branch associated with it, where type 2 removes it. Type 1, if it should fail, if there was no alternate power, the failure could result in the death of the patient. So here's the slide I was referring to. You have normal and alternative power supplies supplying the essential electrical systems. Type 1, you have the 3 channels. You have the life safety, the critical, and the equipment branch, whereas in type 2, you only have the life safety and equipment branch associated with it. So those are the different branches that you're associated with. And let's define each one of the branches. The life safety branch, NFPA defines as healthcare facility fire response is designed around a defend in place concept. However, if evacuation is necessary, the safety branch of the essential system provides power to those functions or warning systems such as alarm systems, illuminated exit signs, lighting as a means of egress, and communication systems needed for safely leaving the building in case of an emergency. So that's a life safety branch. When you talk the critical branch, it serves loads that immediately affect the well-being of patients or are essential to the clinical functionality of the healthcare facility itself. In accordance with the requirements for system functionality, these types of loads are considered part of Category 1 spaces and as such are part of the Type 1 EES. Again, so we've defined these devices as a Category 1 risk factor, and as such we have to use the Type 1 EES in support of them. The equipment branch serves as loads required for the support of clinical activities such as isolation room fans, central suction systems, and in general what this says is that the loads associated with these are much higher as far as a current load, and they have high inrush currents during operation, and because of these high currents the devices are excluded from being connected on a critical branch. So you can't have this equipment branch associated with the critical branch. The loads connected to the equipment branch are necessary for the effective delivery of patient care, so loss of power to this branch will not immediately endanger patients, but it's still necessary to have this backup. When we're talking about multi-modalities, it's really important that we discuss a few factors. Different equipment has different limits. Some of the specifics I'm going to talk about today are going to relate to ultrasound limits. But if you're talking X-ray or portable X-ray as example, they'll be significantly different from what we encounter during ultrasound. So you're going to have to really find out what kind of equipment you're discussing. You're going to have to go to the OEM service manuals and dig into what their specific requirements are. They also, is it a portable system versus hardwired? There are different requirements for those. They specify what the requirements are if they're portable versus hardwired. That's all in NFPA 99 also. So as I said, we're going to use ultrasound as our example today on how to perform an electrical safety test. And I want to point out that I'm going to go through the steps associated with the electrical safety today and the different tests that we have to run on ultrasound. We're going to show you what we need to record and the limits associated with those. I have to discuss these independently so that we can understand the concept of all the tests that need to be performed, but in reality, if you were to do this in the field, you would just have a general checklist, and as you're in a specific mode, which we'll talk about, you would complete all the checks while in that mode, so you're not continuously turning the system on and off to conduct each phase of electrical safety. So let's get started on this. We want to talk about some safety considerations. The standards are used for the electrical safety evaluation of cord-connected, electrically operated patient care equipment. And that's exactly what we're talking about when we talk ultrasound. Safety inspections should be performed at least every 12 months by trained personnel. Now it's important to understand that even though NFPA 99 says at least every 12 months, there may be accreditations out there, such as American College of Radiology, that require these safety inspections be done more often. ACR requires that these electrical safety inspections be conducted every 6 months at a minimum, and goes on to say that if you repair a piece of equipment, a power supply or circuit board, that you should, after that repair, conduct the electrical safety again. So the system under test should not be connected to other electrical equipment or contact with patient or user. That's a pretty big thing, because some of the things we do during electrical safety is actually create an unsafe condition on the equipment or potentially unsafe condition. And we don't want to introduce that to the patient or, in fact, the operator or ourselves. The system, peripherals, and probes should be tested for leakage current. Excessive leakage current can cause injury or death. Well, there's a couple things in this that I find interesting. We have to say excessive leakage can cause injury or death. You know, when we're providing ultrasound or doing an ultrasound, there's a high potential that the patient is already somewhat stressed. Say they have a pacemaker, so they're under conditions that may have already weakened them. So even though the leakage that we're talking about may seem unsafe or not unsafe, in reality we have to be very aware of it. The other thing that I find interesting is I traveled all over the nation to many hospitals, And the one thing that they don't seem to check is the probes. And that's kind of funny to me because that's the one place that we actually take the probe and place it on the patient and give it the path. If in your hospital you're not currently testing your probes, I think you're really opening yourself for some real problems, because that to me is where the rubber meets the road from an electrical safety standpoint. To eliminate the risk of patient being shocked, the customer should. Well, you shouldn't use a damaged probe. What's a damaged probe? It's a probe that the lens is partially missing, the casing's cracked. If you have the ability to test a probe for electrical safety, please do. But even if it passes electrical safety, if it is clearly damaged, it should be removed from service. And you need to check the probe leakage whenever its damage is suspected. But again, I want to clarify that this is no time to leave the probe in service. If you can see it's damaged, whether it passes electrical safety or not, we should remove it from service and get it repaired. So the first step in conducting electrical safety is to make sure your outlet is correctly wired. And specifically today, we're talking about North America requirements. And in that case, we're using the Dell 601 at Conquest right now. The reason we like the Dell 601 is because it allows us to do system safety, electrical safety tests, chassis safety tests, also probe testing, as well as ECG testing. So we really like the Dell 601 in this case because it gives us the functionality to do all three. If you use a different one, some of the terminology may be different, so keep that in mind. Each manufacturer of a device has slightly different naming conventions. But in this case, for the Dell 601, it has a series of 3 lights. And if it's the bottom 2 lights that are on green when you plug it into the wall outlet, it indicates the correct wiring. And I pointed out that the reverse polarity shows the 2 top lights as opposed to the 2 bottom lights. If you have an open ground, it has a single green light in the middle. And if you have the hot and the ground reversed, it gives you the 2 top and bottom lights lit, but the middle one's off. And again, this is on the Dell 601. So there is one condition that we'll talk about again, but I want to point it out that we're looking at is no meter really has the ability to indicate when the ground and the neutral are reversed, because they all go back to the earth ground eventually, which is neutral. And so they can't give you that indication. And we'll talk about this again in just a little while. But the reason I bring it up is if they're reversed, you can get some very unusual electrical safety readings, and it may exceed the limits. And if you've checked everything in the system and you still haven't come up with a solution, then this is a time to go back to your wall outlet and have your facilities people look at the outlet and make sure that it is indeed correctly wired. And here's the lights I was referring to, and here is the actual note that says that you can't test an incorrect wiring between neutral and ground if they're reversed. Next thing we move on to is what we call mains voltage, and again, some manufacturers may refer to it as line voltage, source voltage. It just depends on what meter you're using. But mains voltage is basically the power supplied at the wall. In the U.S. and as far as NFPA 99 is concerned, it's a 3-wire system consisting of hot, neutral, and ground. And neutral and ground are returned to the earth ground at entry into the building. And that's why we can't determine the reverse of the two, because they're essentially the same. To measure line voltage on a Dell 601, you set the function switch to mains voltage. You set the outlet switch to the normal position and power the device under test on. In this case, it'd be the ultrasound system on. After entering imaging, the analyzer will display mains voltage, but under the load of the ultrasound system, What this means is when you actually, in an ultrasound, when you turn the system on, it's not enough to have it on. You actually have to have it actually or actively scanning because that is its highest load condition. And so we want to make sure that you're testing it under load or under its maximum load. And the difference between the line voltages with the ultrasound off and on indicates whether the line is adequate for the device. So if you have a large drop in current or voltage as you turn on the system, what's going to happen is that may indicate that the circuit that you're on has too much load on it, and you may need to have it rewired or introduce a new circuit such that the device, the ultrasound, is isolated on one circuit to limit this voltage drop. Device current is the next thing we want to concern ourselves with. It's the amount used by the ultrasound system, and it needs to be, again, powered on and with actively scanning. And one thing you should do is to go ahead and enter all the different modes, your B mode, your color Doppler mode, your 2D mode, and determine which one gives you the worst condition or the highest reading in this case, and record that highest reading. To measure device current on a 601, Dell 601, set the function switch to current amps, set the outlet switch to normal, and then the L2, which is considered the neutral wire, closed. Power the ultrasound system on and actively image again, and record the reading and monitor changes over time to detect degradation. Two things, again, make sure you're checking when you say actively imaging, all imaging modes. Also, when it says monitor changes over time, it's not enough to just write this down. 6 months later, say it's running at 5 amps today, and 6 months we do another electrical safety check and it's running at 7 amps. There's clearly degradation somewhere, and that's cause to go in and look at what's going on with your ultrasound system. Then we check earth resistance, and earth resistance is a really important one. This is basically measuring the resistance from the system to the wall, and you can do it one of two ways. You can use a digital voltmeter, and just by disconnecting or using ground on the system, you can take the third pin of the attachment plug and a metal part of the chassis and measure the ground resistance. And this is specifically, this requirement for 0.2 was out of a GE manual, and that's because the GE manual specifically says in NFPA standards you have to comply with them. I'd just like to make a note, though. In 2015, this 0.2 ohms was changed by NFPA 99 to 0.5 ohms. So even though now the GE manual says 0.2 ohms, that was based on an old condition of NFPA 99. And we changed, or they changed it to 0.5 ohms because they wanted to match the international standards, the IEC 60601, which was 0.5 ohms. So they went ahead and made the change to increase the ground resistance, but in either case, it should be less than 0.5 in all circumstances. And they want you to check it in more than one place, though. They don't say just any place. They tell you check it in 3 places: from the monitor housing, where there's a metal, exposed metal, rear panel connector, and any caster or wheel support that's, that has metal on it. So it's not just good enough to do one spot on the system. They want you to check multiple spots. And then we talk about the same reading, but instead of using a digital voltmeter, we use the Dell 601. And in order to do this, we turn the system off. We connect the system plug into the Dell 601, 601 into the wall outlet. And when we do that, we want to confirm that, again, our wall outlet is correctly wired with the 2 green lights on the bottom. Once we're clear that we have a good circuit, plug the black chassis cable that's into the top of the meter and connect it to the clamp to the exposed metal part. Most of the time we use the grounding lug on the back for certain systems, certain manufacturers give you specific locations they want you to test it from, and you'll see that on a slide coming up. So we'll talk more about that. Set the Dell 601's function switch to earth resistance position, and then the polarity switch to the off position. Now this is an unusual position. This is kind of a three-position switch, a rocker switch if you will, and the off position is in the middle. So when you're in the middle with it neither normal or reversed, you can then measure the ground resistance. So after we've got our ground resistance, we're going to move on to chassis leakage current test. And this is a really important one. The test measures the current flowing in a grounded person who touched an accessible metal part of the system should the ground wire in the power cord break. So these measurements will be made with the unit on, off, and the polarity normal and reversed. So we need to this complicates things quite a bit. There's a long time where people said you no longer need to concern yourself with reversed polarity versus normal, but NFPA has not removed that requirement, and so we need to make sure we're complying while we do this. Obviously, there's an electrical shock hazard. When you open the ground switch on the safety analyzer, basically, it's removing the safe path to ground, and now any other path it can find, it will use. So you create an unsafe condition or potentially unsafe condition when you do open the ground switch. There is a possibility of equipment damage because, especially if you're using an automated meter or safety analyzer, because some of them don't have program stops allowing you to shut the system down prior to changing polarity, and when you change polarity it will kill power to the system and you'll shut the system down hard. So make sure that prior to changing polarity you do manually shut the system down. Okay, the other thing, just a note on the Dell 601 for those of you who use the Dell 601 is as you're changing from say normal to reverse polarity, they want you to pause in the off position for a minimum of 3 seconds to prevent damage to the actual safety analyzer. So you shut your systems down manually. Once it's down completely, you go from normal to off and leave it in that position for approximately 3 seconds, minimum of 3 seconds, and then go ahead and go to the reverse position before powering it up again. So, and what does that help us with? It confirms the isolation of the power line from the chassis, and the meter is connected to accessible metal parts of the system to ground, and it says parts because they go on to define, later you'll see it in just a slide or two, where they want you to do the safety testing when using a Dell 601. So chassis leakage current test, you turn the system off, plug the Dell 601 into the or the power cord into the Dell 601 and the Dell's power cord into the wall. You then attach a black chassis cable to the connector labeled chassis and the cable clamp to exposed metal part of the system. Again, it defines clearly where they want that to occur. And then you set the function switch to enclosure leakage and measure the respective test points, which are the probe receptacle on the front of the system, wheel support, a metal portion of the wheel support, and a mounting screws from a CRT or LCD housing. Most of our ultrasound systems now have very limited access to metal parts on it to prevent the possibility of getting shocked. So some of these are pretty difficult to actually find and get to while conducting the electrical safety. Then it goes on and says peripherals. Peripherals are optional. They're not optional if they're on the system, but there's no worries if the system doesn't come with a black and white printer or VCR or DVR. You don't need to check, obviously, add anything to check it. These are peripherals that are permanently installed on the system. They want you to check those from an electrical safety perspective also. And then record the results and leave a hard copy with the system. Now here's the data sheet that you'd need to fill out when you're looking at chassis leakage, and it tells you the different conditions. You have to have the unit power on and off, you have to have the polarity switch on normal and reverse, and you have to have your neutral open and close. So you need to test to all these conditions, and this is kind of what I was leading up to at the beginning when I said I have to discuss all the readings that you have to do and all the procedures you have to do independently, but in reality, when you're in the on position in a normal polarity and the open for neutral, you want to do every test while you're in that condition so you're not continuously shutting the system on and off as you go to the different leakage currents and lead-to-lead currents and such. So you need to stay in the one mode and make all your readings. It will save you a tremendous amount of time. So those are your limits. It's chassis leakage limits. You can see they're slightly different from country, USA to other countries. They have again in 2015 made this adjustment so that we're both at 5 milliamps now. So you know, it's up to you how you want to interpret this. If you're using the OEM manual and it says 0.3, that's probably because the manual was wrote prior to 2015. But be aware that these are the current conditions for in 2012. That was the current readings. Then we have to go to isolated patient lead leakage or lead to ground. It depends again on what your specific meter or safety analyzer describes it at, patient lead leakage or lead to ground. So be careful or at least understand what your safety analyzer's verbiage is. This measures the current that would flow to ground through any of the isolated ECG leads. And I know this sounds unusual or I don't mean to insult anybody, but at this point, if you don't have ECGs, you don't conduct these tests. It's clear that way, but I actually have had calls saying, how are we supposed to meet the requirements of this when I don't have an ECG? Well, you don't, just to clarify that. So the meter acts as a patient connected to the system via ECG leads and is grounded to by contacting another grounded surface. As an example, if these leads were connected to a patient and the patient held on to the bed rail that was plugged into the wall and had its own ground, well, there's the simulation of what this is basically acting as. So the measurements, again, will need to be made with the system off and on, polarity normal and reverse, and ground open and closed. It's critical that we do all these different modes or different conditions because you will see as you do these, they do provide significantly different results. So again, we have the possibility of electrical shock. Anytime you open the ground wire or basically disconnect the ground, the system automatically goes and looks for the next easiest place to go to ground. So if there is an unsafe condition that exists on the system, you're part of, you could simply get shocked. So also equipment damage, again, a polarity switch. You can't go from normal to reversed without prior to doing that, shutting the system down manually. Then this lead leakage or lead to ground leakage, you can use Adel 601 again. It has 5 ECG buttons for testing patient leads. Another question I get, well, I only have a 3-lead system. That's okay. You just connect the 3 leads to the tester. Make sure the ground clip is connected to the system's ground terminal. Select the patient lead leakage. That's the position on the Adel 601. And you test each ECG lead. The requirement is you don't have to test all. I do, as a general rule, test all. but NFPA does not have any requirement to test all. In fact, they say exclude it. Test each to the power condition combinations provided, which is on, off, normal, reversed, open, closed, and record the highest leakage current measured for each power selection. So again, as you change these to the different conditions, you'll see significantly different. And so how do you do this? You turn the system off, you plug in your Adel. Again, I have to describe these conditions independently, but in reality, you'd hook the Adel up once and do all your tests while you're in the different conditions. So plug the chassis cable in the chassis connector, clamp to the exposed metal part of the system, connect the patient leads corresponding to the Adel 601, enter into patient lead leakage mode, and select and test each ECG position except all, and record the highest, or record all the combinations, but the one you have to report is the highest or most unsafe condition. And here's the different testing conditions that you have to be in. Again, it's the same as we've seen in the past: on, off, normal, reverse, and open, closed. Record the conditions and report the highest, the most unsafe condition. When you talk about patient lead to ground leakage and patient auxiliary current leakage tests, these are your allowed tolerances: 10 microamps, and at 220/240 it's 500 microamps, or 10 microamps when the ground is closed. So you have your different conditions, and you just need to report and make sure you're inside of the tolerances. Now we're talking patient auxiliary current, which is lead to lead, and this is again an ECG function. This is the patient auxiliary current flows from any patient lead to any other patient lead, and to all other leads for that matter when connected. So that's what you're measuring. Collect the leads to the universal connectors on the front of the analyzer. Function switch to patient auxiliary current, or aux current, and select the leads switch to test individual leads. And again, nothing's changed. You have to make these measurements under on, off, normal, reverse, open, close. So make sure you meet all the requirements of the different meetings or conditions while you're recording your results. Set the function switch. Now we're talking another condition, MAP, patient lead isolation. And this condition is measures the patient lead isolation current. And this is kind of an unsafe, you have to be careful when doing this particular MAP, mains unapplied parts test, because you're actually taking line voltage and applying them to the ECG leads during the test. So you don't want to touch the system or the leads in this condition, because when you do go into the MAP on the rocker switch, you're applying that voltage, and if you're grounded and touching the lead, you're going to get the line voltage. You want to test each ECG lead to the power condition combination. Again, they say accept all. You want to depress a MAP rocker switch and read the isolation current. Now that's when you depress it, that's when the line voltage is applied. So that's when the system is in its most unsafe condition. So be careful where your hands are. If there's somebody working with you, you need to be aware of where they're at on this. And at that point, record the lead isolation current on the data sheet. And here's the data sheet. You have your on, off, normal, reverse conditions, and all your leads are there. Again, all is listed, but they don't make that a requirement. However, I do it. Again, I like to know what the worst case scenario is, so I include all in it. Then we're talking the next three, or the patient lead leakage, and the next one, which is your patient auxiliary current, as well as your MAP. They're all the same tests that you have to run. So as you're in the on, normal, closed position, you should go to each one of those settings on your Adel and just record the readings while you're there, as opposed to doing all of one and then having to start all over and do it again. Do them simultaneously. That way you're not turning the system on and off. So those are your 3 data sheets right there that are required for the conditions that you're testing. Probe leakage current tests. As I said earlier, very few hospitals that I've visited actually go out and physically test all their probes. And I don't understand why. I think this is a very critical portion of electrical safety when it comes to ultrasound. Again, this is where the probes are actually physically contacting the patient. You know, the patient's doesn't normally touch the ultrasound system. So as far as risk to the patient goes, this is where you have the highest possibility of harming a patient. So what is probe leakage? It tests measures the current flow to ground from probes through a patient who's being scanned and becomes grounded, or by touching another grounded surface such as a bed rail that is an electrical bed that is grounded. So at that point, if there is leakage, it'll flow through the patient. Some leakage current is expected on each probe. Small variations in leakage currents are normal. Other variations may be caused by differences in line voltage. It is abnormal if there is no leakage current measured, and the configuration of the equipment should be checked. That's kind of a weird statement in effect. The reason I say it's an unusual is because I've run across where there is no leakage current that is measurable. So I like to point that out, because if you're doing an electrical safety on a probe and you get 0, there's probably some amount of leakage. It's just so small you can't measure it using the meter we have. But in reality, it's normal around, my Dell 601 will be 001, and so my leakage is 1 microamp, and clearly that's intolerant. So if you get 0 leakage on some probes, you're probably okay. But if you get 0 and you've tested several systems and several probes and all you're ever getting is 0, I would start to question the functionality of your safety analyzer. Or if there's, say, 5 probes in one system and all of them are 0, I certainly would check the configuration of your equipment. Measurements will be made with ground open and closed, the polarity normal, and with the unit off and on. Now, notice the difference here. On the system, we had to do polarity normal and reverse. As far as probes are concerned, all we have to do is polarity and normal. So it does remove one of our conditions. We have to do it with it off and on, open and closed, but only with the polarity and normal. So it does remove that condition. And the probe should be active to find the worst case. You want to be actively scanning with a probe, and you want to be testing it in the multiple modes, B mode, M mode, color Doppler, whatever you're checking. You want to find the worst case. When you're talking probe leakage, the probe's imaging area is immersed in a saline solution along with a black chassis clip connected to the dial. In other words, you have an enclosure that has a fluid in it. Saline solution is what they recommend. We don't really use a saline solution. We use tap water. The only thing I say is don't have demineralized water. Clearly, you want the water to be a good conductor, and that's what the saline does for you if you choose to add that. And that's what they ask you to do. They define a saline solution in some manuals. So it's up to how you want to conduct it. As long as it's a good conductor, I've had no differences in readings in using tap water versus a saline solution. And you want to follow the steps right now. You have to test each probe. It's an important concept. You will go into a room and they'll have 2 probes plugged in, and they'll have 5 hanging on the wall. Well, you have to test all 7 of those probes from an electrical safety and imaging perspective. So make sure that you're checking with your customer while you're doing this electrical safety on an ultrasound system to verify the safety of all probes that they have access to. You want to plug the chassis ground into the DAIL, again, on the chassis connector, and attach that to your enclosure that contains the fluid. And then while you put the probe in there, we'll be able to measure the actual current leakage. So you connect the probe under test to the system, put the chassis ground clip and probe's imaging face into the saline bath, and hold on just a second. And after that, do not immerse the probes into solution beyond the level indicated in the probe's user manual. Probe's user manual, if you don't have access to that, you can simply contact us. And bottom line is you need to make sure that the entire face of the probe is submerged. That does not mean the entire probe. I have actually had an in-service where they were asked to clean and electrically safety test the probe, and they in order to clean it, they dumped it entirely into the cleaning solution. So in this case, we just want to make sure that the face scan portion of the probe is submerged in the water. Power on the system booted, depress the lift ground rocker switch, and record the highest reading. Continue with this procedure for all probes, and compare the results with the appropriate table, and you'll see the table to see if the probe passes electrical safety. Provide a hard copy to with the system at the end of your preventative maintenance. Here's the probes tested. You have to do this on each individual probe. So again, I recommend testing, say, the probes while you're in the off, normal, open, closed position. Do all the probes while you're in that condition so you don't have to turn the system on and off, on and off, on and off. It'll save you a significant amount of time. There are two types of probe that are associated with ultrasound. The BF, which is a body floating type probe, it has less, or actually it is less restricted when you talk about the conditions. In a normal condition, you want to have 0.1 milliamps or less. When you open the ground, you want it to stay below 0.5 milliamps. And as you open the neutral, you'll want it to stay below 0.5 milliamps. And again, if you're not familiar with Adel, when you do have the open neutral, when you induce that condition, the system will shut down because you've put an open in the circuit. So make sure prior to opening the neutral that you manually shut the system down. You leave power connected to it, but and a circuit breaker on, but the system can't be on because when you hit L2 open, you'll manually shut or hard shut the system down and can cause damage to your system. Then they have the type CF, which is cardiac floating, and these are much more stringent conditions because the patient, when they're using it, obviously can't report any discomfort because they're under anesthesiology. So we have to be really careful about this, and what you want to do is measure the normal condition, the open ground condition, and the open neutral condition. Again, be careful that you don't do that with the system on. And it gives you the conditions for the United States and other. Notice they're the same, but I do like to point out because there are differences between us and the international, some of the conditions. So what about you've done everything correctly, you've set it all up, you've checked all your conditions, but for whatever reason your leakage still fails. We need to talk about some of the things we can check for when this condition happens. Again, let's say chassis leakage fails. Well, you want to check the ground on the power cord for continuity, and we kind of already said we did that, right, earlier in the presentation, we talked about how to check your power cord for continuity. But if at this point your chassis system leakage is still too high, you may want to go and actually manually disconnect the cord from the system and do another continuity check on the wires to make sure that there's not only the ground wire that may be damaged, but maybe one of the other wires, the hot or neutral, could be damaged also. So make sure at this point that you're checking that as a possibility because your power cord can cause unusual conditions as far as electrical leakage is concerned. Tighten all grounds. Depends what, how the system is grounded, but different systems have it grounded differently, but they say ensure using star washers on all grounded studs so that you're making sure that they have a good connection. Inspect wiring, again, not only on the power cord, but on peripheral power cords, on cabling going to, say, DVR. Make sure you inspect all the wirings and make sure that it's accurate and uptight and there's no damage to it. And one of the things we mentioned earlier is test the wall outlet for proper grounding. If at this point the chassis is failing leakage and you've checked everything that's obvious, well, check the wall outlet. And if you can't do that, because it's really not in your purview, on some hospitals it has to be a facilities person, it should be tested no matter what. And one way you can do it without even worry about testing that particular outlet is take it to a different room, down the hall, somewhere different, and test a different wall outlet on a different circuit and see if that changes your condition at all. If it does, then it's even more likely that the outlet in that particular room is wired incorrectly. So those are some things to check. Well, what about when a probe fails? Well, one of the first things you can do is test it in a different connector to see if it's a problem with a probe and or maybe a connector in the system itself. And if there's no change when you do that, if you have another system, test it on a different system. It makes it real easy. And it says each probe will have some amount of leakage, normally very small leakage, and small variations are normal from probe to probe. So even if you have two identical probes, it doesn't mean that they're going to leak at exactly the same value. And it goes on to say that any variations in line voltage can cause different amounts of leakage. So going to a different system in a different room can cause a variation also. If excessive leakage current is port dependent, it's obviously a system problem, and you should check the connector for bent pins. You can check the probe. Do a thorough inspection of the system because it's obvious if you're changing ports and it changes the value that there's a problem with the system. If problem stays with the probe, remove the probe from service and have it repaired or replaced. This is an important concept. Even if the probe meets or exceeds NFPA 99 standards, it's clear if after you've done as many electrical safety tests on probes as we do, that there's a limit, even if it's meeting electrical safety, that there's still something wrong with the probe. An example is if you see a probe that leaks at 10 microamps, that's high. And at that point, there's no doubt in my mind that there's something wrong with the probe, even though it may meet the standards that the OEM gives you or NFPA gives you. It's clearly not right compared to all the other probes that we've been testing. So at that point, I'll put a comment on the report. Although the M12L probe meets electrical safety requirements, the leakage current is unusually high and it should be removed from service and repaired. I want my customer to know that yes, it passes. I'm not trying to say that it doesn't pass, but I've tested 10,000 probes and I've never, we don't commonly see it this high, so there's something wrong. So I think it's okay to notify your customer when you see this condition even though it passes. What about peripherals? What happens when peripherals fail? Well, the first thing, you can check all grounds and see if star washers are installed on ground lugs and inspect wiring for damage. Same thing we talked about earlier. One thing I'd like to point out while we're talking about this is peripherals can cause an unusual condition while doing electrical safety if they're not connected to the ultrasound system in a correct manner. What do I mean by that? Let's talk about like a black and white printer. If the customer has a black and white printer connected to the ultrasound system but plugged into the wall, it bypasses the isolation transformer and will give you incorrect readings. And so in reality, what happens is the customer themselves have created that unsafe condition, and you as clinical engineers, biomeds, need to recognize that and correctly wire that, plug it in to the outlet associated with the system on the system such that it's isolated. One of the clear places this gets abused is in OBGYN or labor and delivery, where they're scanning the mother and the mom wants to see her baby on an external monitor. So what they do is they take the video out, run it over to an external monitor and plug that external monitor into the wall, and that creates an unsafe condition. If you're going to do that, you need to make sure that you have a medical grade isolation transformer for that monitor, that TV, to plug into so that it stays isolated from that end also. Otherwise, you're creating this unsafe condition. After all of that, you're still failing electrical safety. You're going to have to start isolating the different portions of the ultrasound system. Remove one probe at a time. Remove the peripherals so that they're not part of what's of the circuit. As you're doing that, remove them one at a time and see which condition actually, if any, puts you back in electrical safe in an electrically safe condition. So you do them one at a time to try to figure out which device is causing it, and then go back and check that device. All right, that's what I have today as far as NFPA 99 is concerned. I want to thank you all for being here, and I'd like to open up the floor for questions.
Thank you, Jim. We do have some questions that have come through while you were going through your presentation. The first one we're going to go ahead and start with is NFPA 99 the only standard that addresses electrical safety?
And the answer to that is no. NFPA 99 is not the only one. They have NFPA 70 for when they're actually initially installing a product. They also have other electrical standards that don't necessarily apply to medical devices, but NFPA 99 does address the medical devices portion of electrical safety after it's been installed. So there are other standards that are out there.
Great, thank you. What is the best way to review the NFPA 99 standard?
Well, that's an interesting question. Obviously, you can go right out to the NFPA 99, NFPA website and look up NFPA 99, which is the addressing the medical devices, and they have a free PDF that you can review as long as you become a member, which is no cost, as I recall, no cost associated with it. If there is a cost, it's minimal. The other thing that we did here is they have a handbook, if you will, that you can buy or purchase, and it's a little costly, I think $170. But what I like about that over just the NFPA guideline itself is that it specifically tells you what changes have been made. So if 2012 to 2015 a change is made, it highlights it in addition to just showing you the entire regulation.
Very good. We have another question here. Do all OEMs require NFPA 99 electrical safety tests to be accomplished?
No. From an ultrasound perspective, as an example, OEMs don't always specify what their criteria for electrical safety are. Philips for the IU22, IE33, they don't dictate what standard that you have to comply with. Where GE, for example, is very, very specific that we are conforming to NFPA 99 and that's mandatory while conducting electrical safety tests on it. So each OEM has different or has their own criteria. However, I highly recommend as you're working on medical equipment, especially category 1 and 2, that you do conduct NFPA 99 or the International 60601 safety testing on them, because it's the right way to do it.
Great. Our next question here, is there a limit on how much leakage from the probes is acceptable?
Yes, and I covered that in the latter part of the presentation. There's a difference between the BF, which is body floating probe, versus a cardiac floating, which is your TEE probes that are internal. So there are limits, and if at any point anybody's confused as to those limits, we can certainly help them out. They can call us on our tech support line, and we can provide those limits for OEM-specific probes.
Okay, the next question. How do you test the leak current and cable continuity on an equipment with an isolated power block?
And that's tough. You can't. That is one of the downfalls of some of the portable pieces of equipment. They do have that isolated transformer, and there's no grounding lug. And in reality, at that point, the manufacturer itself will tell you that electrical safety from an NFPA perspective is not possible to do. However, you can still test the leakage of a probe while having an external transformer on a portable device, as an example.
Okay, thank you. Next question, what is the current version of NFPA 99 that the Joint Commission recognizes, and is it also accepted by CMS?
The current version is 2015. I don't have it. Nowhere in the NFPA 99 does it say that that's the one the Joint Commission uses, but I would assume it is. 2012 was a version before that, and 2015 removed some of the criteria and added others. So I would say 2015 is the current version, and that's the one the Joint Commission would follow.
Great. And I think you just answered this question. What year or version of NFPA are you working with? You said that was 2015. 15. Okay.
Right now, the next version that they're working on, there's no way to say that it'll come out when they plan, but it's 2018 is the next revision that is supposed to come out, and they like to do it every 3 years. So.
Okay, the next question. What issues have you noted for testing with a probe leakage tester as opposed to having it connected, what issues have you noted for testing with a probe leakage tester as opposed to having it connected to an ultrasound machine and using an ESA?
We only do the one condition, which is connected to the ultrasound, because in the field, that's the way it's going to be used, if you will. So we tested it in what we consider to be the most used condition, which is attached to the ultrasound system, and the manufacturers will give you both choices, at least the ones that we've talked about, GE as an example for ultrasound, tell you how to test it in both environments. I just prefer to test it in the environment where the patient's going to be affected.
Great, and since we're nearing the end here, we'll answer one more question. Anyone else who submitted questions that we didn't get to today, Conquest will get a copy of all of those questions and we'll follow up with you post-webinar. So our last question here, on the EKGs, most of them come with plastic cases, but we need to test the current from leads to ground, but there are no metal points to test. How can we test them?
Well, that's where your safety analyzer gives you the option of connecting right to basically the safety analyzer on a metal point. If I'm understanding the question correctly, the metal points that you attach are going to the actual safety analyzer itself.
Great. Thank you for answering all those questions, Jim. Like I mentioned, if we didn't get to your questions, Conquest will follow up with those directly. Thank you to Jim, and again to today's sponsor, Conquest Imaging. One lucky attendee will win lunch for their entire department. Details are included in the post-webinar survey, which will appear on your screen shortly. You must complete the survey to obtain your certificate of attendance. If you do not see the survey at the conclusion of today's webinar, please email us at webinar@mdpublishing.com. Thanks again, everyone, and until next time.